Welcome to a video on second order partial derivatives. Just like we're able to determine higher order derivatives of a function in one variable, we can also determine higher order partial derivatives of functions in two or more variables. And since there are two first order partial derivatives of functions of two variables, there are going to be four second order partial derivatives of functions of two variables. And the notation used for second order partial derivatives is very important. Let's go ahead and take a look at that. All the notation here is telling us to find the partial derivative with respect to x twice. Similarly, the notation here is telling us to find the partial derivative with respect to y two times. Now these next two can be a little tricky at first. All the notation here is telling us to find the partial derivative with respect to x and then the partial derivative with respect to y in that order. So looking at these first two notations, we work our way from right to left. We find the partial with respect to x and then with respect to y in both cases. Now looking at these last three notations, we find the partial with respect to x and then with respect to y again, but notice how the order of this notation here is now from left to right, and over here it's right to left. So we differentiate with respect to x first and then with respect to y. And then here the notation has reversed to find the partial derivative with respect to y first and then with respect to x. So we need to make sure that we're aware of the differences here. And sometimes these last two are called the second order mixed partial derivatives. Let's talk about the geometric interpretation of the second order partial derivatives. Sometimes we'll just say fxx and fyy for these second order partials. If fxx is greater than 0, then the function is concave up in the x direction, which means if it's negative it'll be concave down. And if fyy is positive, then f of xy is concave up in the y direction. And again, if it's negative, it'll be concave down. In general, mixed partials tell us how a partial in one variable is changing in the direction of the other. So if we have fxy, this tells us how the rate of change of f of xy in the x direction is changing as we move in the y direction. Let's take a look at a graphic that illustrates these first two referring to concavity. Right now we have fxx and fyy are both positive, meaning in the x direction, as we see here, the surface is concave up, as well as in the y direction, as we see here. Now let's go ahead and change it so that fxx is negative and fyy remains positive. So in the x direction, you can see now it's concave down, and the y direction it's still concave up. Now let's go ahead and make fxx positive and fyy negative. So now in the x direction you can see it's concave up, and the y direction it is concave down. Let's go and take a look at some examples to get some practice on finding second order partial derivatives. Before we do that, we have to find the first order partial derivatives. So the first partial with respect to x will treat y as a constant. We'll have 8x to the third minus 15x squared y to the third. This should be 0. First partial with respect to y, we'd have 0 here, negative 15 x cubed y squared minus 4y cubed. Now let's go ahead and find all four second order partial derivatives. So here we're going to take this first partial derivative and differentiate again with respect to x. So we'll have 24x squared minus 30x to the first, y to the third. For fyy, we're going to find the derivative of this with respect to y again. So we're going to have negative 30x cubed y to the first minus 12y squared. Now for this mixed partial, we'll find the partial derivative with respect to x and then with respect to y. So here's the partial with respect to x, and now we'll differentiate this with respect to y, treating x as a constant. So this would be 0, and this would be multiplied by 3. We're going to get negative 45x squared and then y squared. And now here we'll differentiate the first partial with respect to y with respect to x. So we'll multiply by 3, negative 45x squared y squared. And here we're differentiating with respect to x, so this would be 0. One thing you'll notice is, if you take a look at the two mixed partials, they're equal to each other. And in fact, they will always be equal to each other. So let's go ahead and state that. These two mixed partials will always be equal as long as they are continuous over a specific region. So in the future, if we find one of these, we also know the other. Let's take a look at one more example that's a little bit more involved. We'll start by determining our first order partial derivatives. So the first partial with respect to x is going to require the product rule. So we'll have x times the derivative of exy squared. So we'll have exy squared times u prime. Treating y as a constant, we'll just get y squared plus the second times the derivative of the first. That'll just be 1. Let's go ahead and clean this up. Notice the exponential is a common factor. Let's go ahead and factor that out. So we'll be left with x y squared and then plus 1. Let's go ahead and determine the first partial with respect to y. So we're treating x as a constant, so we'll just have x e to the xy squared times u prime. So the derivative of the exponent with respect to y would just be 2xy. Let's clean this up. So we have 2x squared y e to the xy squared. Now let's go ahead and find our second order partials. So for fxx, we'll differentiate this with respect to x again, treating y as a constant. So it's going to require the product rule times the derivative of the second with respect to x. So we'll have y squared and then 0 plus the second times the derivative of the first, again with respect to x. So we'll have exy squared. The derivative of the exponent with respect to x is going to be y squared. Let's go ahead and clean this up. We're going to have to distribute here and here. Notice the second distribution, we're going to have another y squared e to the xy squared, and we have another one here. So we're actually going to have two of those. And then we'll have x y to the fourth e to the xy squared. To determine fyy, I'm going to go ahead and find the partial derivative of this with respect to y again. So notice we will have to apply that product rule again. So we'll have the first times the derivative of the second. So we'll have exy squared times u prime. So we'll have 2xy plus the second times the derivative of the first with respect to y. That'll give us 2x squared. So it looks like we're going to have 4x cubed y squared e to the xy squared. And here we'll have plus 2x squared e to the xy squared. I could factor this, but I'm going to go ahead and leave it like that. Let's go ahead and copy these first order partials on the next slide, and then we'll find the second order mixed partials. Remember, we discovered earlier that these are going to be equal to each other, so we can really just find one of them. Let's go ahead and find this mixed partial, and then we'll also know the other one. So we're going to go ahead and take this first partial with respect to x, and then differentiate it again with respect to y, treating x as a constant. So again, we'll have the product rule. We'll have exy squared times the derivative of this with respect to y. So we'll have 2xy plus the second times the derivative of the exponential. So we'll have exy squared times the derivative of the exponent with respect to y will be 2xy. Here Here we have to distribute. Looking at the second distribution, we'll have 2xy e to the xy. We have another one here. So we'll have 4xy e to the xy squared. Then we'll have plus 2x squared y cubed e to the xy squared. And again, we know these are equal, so I'm going to go ahead and just state that these are equal. And that's going to have to do it for this video. I hope you found these examples helpful.